Okay, so this is the outline of chapter 31. So first we'll introduce LC oscillator, and then we'll talk about the damped oscillation in the RLC circuit. So this is a more complicated one than the LC oscillation. So for the LC oscillation, we do not assume there are any energy loss. So for the damped oscillation, there is the resistor to absorb some of the energy. Okay, and then we will talk about the forced oscillation of the free simple circuit, which means we will talk about the phasor. Maybe we should have learned it in high school physics, but I'm not sure. And then we'll talk about RLCs in series, and then the power in AC circuit, and then also the transformers. Okay, so this is the LC circuit. Okay, you can see there are 8 figures here. So let's start from this one. Okay, we have LC. We assume it already stores some energy, let's say in the capacitor only. Okay, for the capacitor, if you still remember, UE is 1/2 CV squared. If you still remember, for the L, UB will be 1/2 LI squared. Hope you still remember this thing. Okay, so we assume that if at the beginning all of the energy are stored in the capacitor, so which means that there is no current, only the voltage across the capacitor. Okay, so in that case, the energy of the capacitor will try to go out and then charge in the inductor. Okay, so there will be current in this direction, like counterclockwise. So yeah, UE will decrease and then UB will increase, because when there are some current going out, these charges will reduce. The charge here will reduce, which means that the voltage will reduce, which means that the the UE will start to decrease. And and at the same time, simultaneously, UB will increase because there is current going through it. Okay, so at a certain moment, UE and UB will be equal to each other. But of course, it is increasing dynamically. Okay, so there will be some energy stored in the magnetic field, and then there's some energy stored in the electric field. And then some time later, all the energy stored in the capacitor will go to the inductor. So UB is maximized, UE is 0. And then sometimes later, it will even go forward. Okay, at this moment, the current is maximized. In this direction. But later, I will still keeping in this direction, but I will start to decrease. So in that case, you can see this is positive for the top plate, but here, positive for the bottom plate. Okay, so still some current going in this direction to charge the bottom plate. But yeah, here we have V squared. So even though V is like a negative value, so V squared is still positive. So energy is always positive. Okay, so like this. Okay, so for a specific moment, UB and UE will be equal to each other. And then later on, all the energy go to the capacitor. So these two figures looks alike, but the only difference is that positive for the for the top plate, this is positive for the bottom plate. And then it will still move forward, okay, going back. Okay, so this is like so this is actually an oscillation. And then going back to here, and then loop again, back and forth. And then as much as we do not assume any resistance for this circuit, okay, it will just oscillate forever. Okay, so it just mentioned that UE to be Q squared over C, or I just mentioned 1/2 CV squared. So actually these two are the same. You just need to use Q equals CV to change the variable. These two are equivalent to each other. And of course, UB is 1/2 of LI squared, so nothing special. Okay, so here it mentioned that if we have a LC oscillator, we have something like this: 1/2 Q square over C, and then for the inductor 1/2 Li squared, and then it try to analogy to the mechanical spring mesh system. In the textbook, it called it box spring system. I usually call it a spring mesh system. Spring mesh system. So just a name doesn't really matter. Just call it box spring. Okay, spring mesh may be easier to pronounce. Okay, so for the spring, the energy stored in the spring is the 1/2 kx squared, is the Hooke's law. And then for the block, the kinetic energy is 1/2 mv squared. Okay, so you can see these are the analogy. You compare this one to this one, this one to this one, and then this one is another derivative of I equals dq dt. This is v equals dx dt. This is the velocity or the speed. Okay, so you just try to correlate all the things, then you will get, okay, there will be oscillation frequency, or frequency of oscillation. Okay, so here we try to see how to derive. Okay, of course, even in high school physics, you know, for the oscillation, it is just like a cosine or sine. So why is like that? Why it must be a cosine? Okay, so here let's see. So here we have the total energy UB plus UE, and then yeah, so there's nothing else to store the energy. So we only have VB, UB and UE sum up to be the total energy. This is the total energy to be 1/2 Li squared plus 1/2 Q squared over C. And then as much as we have no resistance or no energy loss, so which means that du dt should be 0. So which means that this is actually the conservation of energy. So we try to take the derivative here, which means we try to take the derivative of this thing. Okay, so this is L. L is a constant, so we just take the derivative of I squared. So I squared will be 2I. 2 and 1/2 will cancel each other. So we have L times I. And don't forget the chain rule. We still need to take the derivative of the I itself. So we have di dt. So this is due to the chain rule. And then for the second one, Q squared over 2C. C is a constant, so we just put it there. And then take the derivative of Q. Q squared. Q squared will be 2Q. 2 and 1/2 will cancel each other. So we only have Q here. And then similarly, this is also due to the chain rule. Okay, and equal to 0 is actually this one. So we have this one. We have a differential equation. Okay, so here we also try to actually these two variables I and Q are dependent to each other, which means that we have I equals dq dt. So we just try to substitute I to be dq dt, and then we can get, also we take derivative on both sides. We have di dt to be the second derivative of Q. Okay, so we can just substitute I to be dq dt, and then di dt to be second derivative of Q. So we will have L and then dq dt, and then times the second derivative of Q plus Q over C times dq dt, like this. So we can just do the cancellation. We just assume that dq dt is not always equal to 0, then we can just cancel it. And then finally, we can just divide L on both sides. So L and L cancel. So we have the second derivative of Q plus 1 over LC. So we just distribute this here, 1 over LC and then times Q. So Q is a variable, so we just move it to the back. So we can see this is the second derivative. This is the original function. Okay, that's the point. Yeah, so this is the energy method. Actually, I think this method is quite interesting, but I don't think I learned this method before. Yeah, when I learned the circuit theory, I have never saw this. I have never seen this method. When I try to prepare to teach this course, it's first time to see this method. So actually, previously when I learned the circuit, I used the potential method. The potential method is just like this is L, this is C. Okay, so this is VC plus, and then this is VL plus minus, and then with the I. Okay, so of course we have VL equals L di dt, and then also we have I equals C dVc dt. Okay, so still we use the KVL. So we have, this is VL plus VC to be 0. Okay, so here, this I, we can actually put this thing into here. So we should have LC d second derivative of VC like this. Okay, so we can just plug in this one to there. So this is VL, this is VL. Now VC plus VC. VL plus VC equals 0. Okay, so this is VL. We can just plug it LC D2 VC DT2 plus VC to be 0. And then we can just divide LC on both sides. We can have D2 VC DT2 plus 1 over LC VC equals 0, like this. Okay, so we have a same second order ODE. Okay, this is a second derivative, this is the original function, this is 1 over LC equals 0. Oh, but you find that this is Q, this is not VC. But actually you can do some change of variable. You can finally find that they will be the same thing, because yeah, this is actually I equals dq dt, and then I also equals C dVc dt. So actually if you try to take some derivative, and then you multiply the C, and then you can just actually substitute Q to be VC with the same coefficient. This is a property of the linear system. For the linear system, so when you try to plug a variable in the circuit, let's say we have VL VC, you can also write a D2 VL dt plus 1 over VL to be 0, or you can also write a D2I dt2 plus 1 over LCI to be 0. Okay, so this is the signature of the linear system. So the coefficient don't change. You can just change the variable. They will have the same expression. Of course, with the different initial value, the solution might be a little bit different. Just like we will have something like exponential to negative or something, or maybe a constant minus the exponential something. Of course, this is a second order. The solution is different. Okay, maybe let's consider it next time. Okay, so yeah, maybe I can quickly tell you. Yeah, actually, this is a second order, so we change it to S squared and then plus 1 over LC. This is VC. We change it to 1 equals 0. So we have S to be plus or minus 1 over square root of LC, and then multiplied by J. J is negative of square root of 1. Okay, so we have complex conjugate root, which means that the solution should be let's say VC to be A cosine of T over square root of LC plus B times sine of T over square root of LC. Or you can just assume that this is the omega equals 1 over square root of LC, so that we have something like A cosine omega T plus B sine omega T. Okay, you can see the solution only have a cosine or like this. Actually, this is the trigonometry identity. You can just change it to the polar coordinate. Okay, hope you still remember in the high school trigonometry. You can just make it like this is cosine phi, this is sine of phi. Okay, then it can be like a cosine of cosine omega t minus phi, something like this. It depends on how you determine the it doesn't really matter this is plus or minus, but yeah, if it is a plus sign or this is a minus, but it doesn't really matter to be make it a plus sign. So they are the same thing, so that's why the solution look like this. Okay, so let me stop here today, and I'll see you on Friday.